Let's take a quick look at two sets of classic algorithms, searching and sorting algorithms. In computer programming, we often explore these two groups of algorithms, searching and sorting, in order to dive deeper into algorithm creation and evaluation. In both cases, there are a variety of algorithms that can successfully complete the searching or sorting task, but not all of them have the same efficiency or clarity. Let's take a look at this example of a list of numbers. Say we want to find the occurrence of a specific number. One technique or algorithm that we could use is a random search. In this case, we just randomly look around trying to find our desired number. Because it's random, it may take a long time to find our number. Another algorithm we could follow is a linear search. This method will search down the line looking for our number in an organized way. This may still take a long time, but at least we'll know we've looked through every number in the list. Now what if we could sort the list first? Then we could apply an algorithm like a binary search. Then if we know we are looking for a number that is greater or less than the midpoint of this sorted list, we could search that half of the list. For example, let's say we are looking for a 6. That value is greater than our midpoint, which in this case is after the third row, so we could start there and look linearly from this point. Now, of course, there are even different algorithms to sort the list as well. There's one called bubble sort that compares two numbers next to each other, and if one is out of order, it swaps them. Like right here. And we keep going. The 2 is less than the 9, so we swap them as well. This process of swapping lower numbers to the left would keep going through the entire list. Then it would start over and go through the list again, eventually sorting the list in its entirety. Selection sort is a different algorithm that looks for the minimum value in a selection, in this case our list of numbers, swapping that value to the front of the list. To start, 1 is in the front of the list, so we are comparing every value to 1 until we find one that is less than it. Since 5 is greater than 1, it keeps going. 2 is still greater than 1, so we keep going, etc. Eventually finding the 0 in the second row, and since that is less than 1, it swaps the two numbers, moving the 0 to the front of the list. The process continues until you reach the end of the list, at which point it knows now that the lowest value is at the start of the list. Now it starts over, completing the same process, comparing every number to the second value in the list, which is the 5. Insertion sort moves from left to right, sorting a number into the correct spot of the numbers to its left. 5 is greater than 1, so it leaves it. The second 5 is still in the correct location in regards to the 1 and 5 to its left. The 2, however, is not in the correct spot relative to the 1, 5, and 5 to its left, so it begins to move it left. When 2 reaches this location, it stops, because it is now in the correct position relative to these 4 numbers. And the process would continue with the next number. As you can tell, there are many scenarios in which more than one algorithm can correctly solve a problem. We want to begin to think about efficiency and clarity of these algorithms to help us decide which to use in our programs. Now it's your turn to dive deeper into comparing different algorithms.